Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at entropy. Specifically, we're going to be trying to connect this idea of entropy as a way of determining whether or not something is favorable with this idea of entropy as a measure of disorder. So one of the big things that's really going to be useful if we're trying to look at entropy is to go down to a kind of a small level. So most of the ways we can think about chemistry is by looking at it as a whole bunch of little particles and molecules all behaving independently. And when we zoom out, we can see how these behaviors tend to work together. So when we do this, what we can do is try and approximate some very common chemical phenomena as simple processes. So let's say I've got a molecule that can be in one of two states. Each one is equally likely. In this case, what we can do is represent the system as essentially a coin toss. It can be up or it could be down. There's lots of processes that tend to occur this way, the most common being the orientation of electrons. So if I've got a system that can be in one of two states, both equally as likely, I can go ahead and treat it as a coin toss. If I've got 10 of such of these particles, I'd expect equal numbers to be heads and equal numbers to be tails. And we can demonstrate this using something called the number of microstates. So this is a statistical way of talking about the number of ways an outcome can occur. So if I was going to toss 10 heads, there's only one way that can occur. There's also only one way I can get 10 tails. As a result, these are very unlikely. However, there are a lot of different ways I can get 5 heads and 5 tails. So as a result, that's the one we're most likely to see. The further away we get from that, less likely we are to see that occursion. So generally, we're going to expect to see a system with the most number of microstates. So the most possible ways it can occur. So what we can do is try and move from this language of microstates to entropy. And that's really possible using what's called the Boltzmann definition of entropy. What it says is that the entropy of a system is going to be related to a constant called the Boltzmann's constant times the natural log of the number of microstates. So again, this does still preserve this idea that the more ways something can occur, the more likely I am to see it, as I'm going to have a higher entropy. The Boltzmann's constant really can kind of be seen as unit conversion, because our entropy will typically have units of joules per Kelvin or potentially joules per mole Kelvin, whether we're talking about absolute entropy or molar entropy, which we'll deal with much more later. So the Boltzmann constant itself kind of seems like a weird number, but it turns out it's actually a number you might be familiar with. It's essentially the ideal gas constant divided by Avogadro's number. Because remember, the ideal gas constant is in joules per mole Kelvin. So if we turn it from the entropy per mole to the entropy per molecule, it turns out you get the Boltzmann constant. And as a result, anytime you're looking at something that includes the Boltzmann constant or the ideal gas constant, this is an indication that entropy plays a big role in determining how that property works. So that explains kind of the Boltzmann constant portion of this. But what about that natural log? Why do we use natural log and not just the number of microstates? Well, one of the reasons why is we want to keep the relative likelihood of a given arrangement not really depending on the size of the system. So for example, if I toss 10 coins, I'm going to be fairly likely to have 40% of them be tails. However, if I toss 200 coins, that starts becoming a lot less likely, as we tend to see much more of the system at that 50-50 mark. And as the size of the sample gets bigger and bigger and bigger, this becomes more pronounced. And as a result, this can get kind of out of hand by the time you hit molecular size systems, which have moles of particles. So that's 10 to the 23rd. And that's just a little unmanageable. In comparison, if we use the natural log, it really doesn't depend on the size of the system. The entropy will increase as W increases, but the relative entropy will stay the same whether I've got 10 particles, 200 particles, or a mole of particles. We're going to still have the same ratio of the difference in the natural log of our microstates from 0 to the 50-50 mark either way. And this gives us a very robust way of talking about how much more or less likely I am to have a certain probability of distributions. And as a result, we're going to tend to focus a lot less on the number of microstates, and instead we're going to continue using this language of entropy. However, I will occasionally go back to microstates to illustrate essentially how something becomes more or less ordered or disordered, or again, how much flexibility a system has. But for now on, we're not going to use the number of microstates mathematically, but much more conceptually. However, we can also still use this Boltzmann distribution, as I said, to illustrate some fairly cool properties. So we're going to hang on to W just for a couple illustrative examples. So the first thing that is really important to note is that entropy will be additive. So if I have two different systems and I want to find the total entropy, I can get that by adding the entropy of system A and system B. And we can show this using the fact that, according to statistics, the number of microstates will be multiplicative. So this means that the total number of microstates for a combined system will be the same as the number of microstates for A times the number of microstates for B. Then we can go ahead and use the property of natural logs to say, well, natural log of A times B is the same as natural log of A plus the natural log of B. Then we go ahead and distribute out our Boltzmann constant, and ta-da, we prove that the entropy for a total system is going to be the same as the entropy for each of the individual systems added together. We can also use the same basic principle to show that entropy is size extensive. So that means that essentially it depends upon the size of the system. And a good way to illustrate this is if we look at what happens when I double the size of a system. So based on what we have previously known, if I double the size of the system, that means I pretty much have two system A's. And as a result, our number of microstates is going to be the original number squared. So using this, we can show that the entropy is going to be the Boltzmann constant times the natural log of the square of our microstates. Now we're going to continue using some fun properties of natural logs. And it turns out you can use the exponent inside a natural log and remove it by pulling it out in front. So this now becomes twice the Boltzmann constant times our original natural log of the microstates. As a result, it means that the entropy for our new total system is going to be twice the entropy of the original system. So again, you double the system, you double the number of microstates. This does end up providing some issues. As you've seen last semester, we much prefer having size intensive properties where we don't have to worry about how big or small the system is. So we can do the same thing we did last semester. If we have a property that's size extensive and I want to make it intensive, we divide it by another size extensive property. Our classic favorite here is going to be moles. So sometimes you'll hear me talking about entropy, and sometimes you'll hear me talking about molar entropy, depending on whether or not I care about the size of the system. So I do want to make sure you watch out. Again, just like last semester, sometimes your book can be a little bit lazy, and they'll use S when they're actually talking about the molar entropy. But as always, keep an eye on the units. Is it joules per Kelvin or joules per mole Kelvin? And that will help illustrate which one you're using. So one of the cool things we can do is, now that we know our system is size extensive, we can show that, again, if I increase the number of molecules or the volume in the system, then that means the entropy should increase. Because again, I'm going to, if I double the system, I'll double the microstates and thus, or I'll square the microstates and thus double the entropy. So a classic example of this is if I go ahead and take a bulb of gas and I go ahead and release it and let it enter a vacuum, I've essentially doubled the volume the system can occupy. And as a result, because I've got more room for those molecules to move around in, I'm going to have many more microstates or arrangements of these molecules because there's more places they can be. And as a result, this is one of the classic easy ways to increase the entropy of a system. You go ahead and just let a system expand. This is the reason why if you go ahead and put a whole bunch of work in blowing up a balloon and you release the edge, that gas immediately leaves. And the reason why is it maximizes entropy. This is one of the reasons why entropy is often said to express the desire of matter to spread out, as well as why entropy is referred to as a metric of disorder, because it wants the most possibilities it can get, which means spreading everything out as far as possible. So next time, we're going to focus a little bit more on some other ways we can increase or decrease the entropy of a system. Until then, take care.